Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is Schiff Base chemistry. So we shall discuss today about the preparation of Schiff Base and of its chemical reaction and finally application in modern science. So lots of chemistry to be learned in this video, but before going to details, one MCQ. What is the major product of this reaction? I request you please pause the video, write your answer in the comment box, and definitely at the end of the discussion we will get the right answer. Student, please try, because remember, self-evaluation is essential for improvement. Now let's come to our main topic, that is Schiff Base. Now question, what is Schiff Base actually? Now Schiff Base is actually a compound, means which is named after scientist Hugo Schiff, with general structure of R1, R2, C, Rn3. You can see the structure. They can be considered as a subclass of imine. So this is the structure of Schiff Base. Since they are subclass of imine, so let's learn what imine actually is, then concept will be clear. An imine is a functional group or chemical compound containing carbon-nitrogen bond. The nitrogen atom can be attached to either hydrogen or organic group. So if this group is not a hydrogen atom, then this compound sometimes referred as Schiff Base. So now you get the difference. Difference is here. If this R group is hydrogen, then it's imine, and if this is R, means alkyl, aryl, whatever other than hydrogen, then it is called a Schiff Base. So this is the main difference. And what happens actually, student, remember one trick how to make Schiff Base. Just it is a Schiff Base, means imine, how it prepare. So there are two hydrogen, where this oxygen, just remove these as water, okay, and in this way nitrogen and carbon will have a double bond, because nitrogen valency is 3. So in these ways you can draw Schiff Base easily less than 10 seconds. So this is the tricks. Now let's discuss about the mechanism. It is acid catalyzed Schiff Base formation, because Schiff Base you can form by two ways. First acid catalyzed, second is base catalyzed. So now let's discuss the first one. Now if you put acid H plus, then there are two chances. Either this amine can form, means amine can act as a base, or this LD, means aldehyde or ketone. In this case I have shown aldehyde will protonate. Now question, who is relatively more basic? Still reaction why happens on protonation on this? Actually everything happens in the reaction medium, and this protonation is a reversible process. I am actually shown that step which is involved in the mechanism. There are other many steps, but we will not consider since they are not resulting the final product. Okay, and we know this aldehyde or ketone, they are actually electrophilic, means this carbon is delta positive, and right now after protonation their electrophilicity increases, means you can see this structure, or you can draw a canonical form where you can see this is the R, C, OH, and positive charge is in here. So from this canonical form you can clearly see that after protonation the electron efficiency or electrophilicity at this carbonyl carbon increases significantly. Consequently this nitrogen lone pair or this amine lone pair attacks here and opens it up. Subsequently it produces an addition product with carbonyl. Now see, after addition this nitrogen is having a formal positive charge. So what happens? It releases one proton and became neutral. Point number 1. In the second step what happens? There is lone pair in oxygen atom. So that oxygen atom abstract that proton. So this step is proton elimination from nitrogen and proton addition to oxygen atom to the lone pair. So ultimately it will produce this. Now question, why this is important? Because this water will leave, and see, OH in acidic medium is not a good living group, but it could be good living group if it converted into this OH2 plus, because positive charge. Now what happens if this group pushes, this lone pair pushes here, it will come. Now what happening actually water is eliminating, so it's a neutral molecule, so that's why it means it's stable. So that's why reaction will happen at this position, and in this way it will produce still a iminium complex. So imine, yum means protonated. Now basic workup will result in this amine. Now why this is? First of all, this is protonated. Second, the medium is actually student acidic, so this species will be the end product if you don't do the base mediated workup. Base, what you will do, this base will abstract this proton and ultimately free imine you will get, or you may consider it's a Schiff Base if what I said R1 is not equal to hydrogen. Similar mechanism if you check base catalyzed. So what happens here? In the base catalyzed reaction, in first step this reaction will happen, and remember everything, this all the steps I have shown in front arrow, but this nucleophilic addition, these actually are reversible stage. Okay, so in first stage it will attack and it will open up. Now you can say that, sir, if sometime before you told that after protonation it happens efficiently, it's true that after protonation reaction happens very efficiently, but reaction happens in the second step. This base will work. How? After addition it will produce this O minus N plus. So in the next step what you can expect? In next step means next step you can expect that in presence of base, first this proton will be abstracted, and another thing, after abstraction of this proton what it will produce? Water, and that water will be protonate this oxygen. So it will produce this amino alcohol derivative, addition product, simple. But in the next step the role of base comes, because see this base abstract proton from this proton. Now you can say that, sir, why are you saying this proton? Because oxygen is more electronegative, so this OH proton should be abstracted. It's true, but it will not result anything. Okay, so I am talking about that which will result in the chemical reaction. So now next step it will come and it will leave. So in this case OH is leaving. So the first is protonation, and it will produce this nitrogen anion, and second this nitrogen anion push, it will leave. So in this way, first step there was a proton elimination, means in this case proton elimination, in second step OH elimination, so overall water elimination. So in this way this is directly produce imine, and you may consider it's a water. Now why directly free imine is here? Because the medium is basic. So this is the overall thing, and please remember both H plus and alkali both are needed in catalytic amount. So catalytic amount of acid and base is sufficient to carry out this Schiff base formation. Now, so in this context there are two types of carbonyl, student, means this is one ketone and another one is aldehyde. So if I ask you which is more efficient for this Schiff base formation, obviously aldehydes. That's why in majority of cases you see the example of aldehydes. Point number one. Why? Because first of all the electron deficiency of aldehyde carbon is more, because it is attached to hydrogen which do not have plus I effect. Second thing, there are two alkyl groups, so bulkness around this carbonyl carbon is more, whereas in aldehyde bulkness around this carbonyl carbon is relatively less, and this is the concept of Borgi-Dunich trajectory or Bargi-Dunich trajectory, where near about 107° angle this nucleophilic attack happens. I have already discussed, you may visit for better understanding. Now let's come to the second part, that is different type of amines. You can say this is actually an aromatic amine, aliphatic amine, and this is aromatic amine. Now from this thing you can directly say that, sir, aliphatic amines are more electron rich, so they will do reaction more efficiently. It's true, but remember in case of aromatic amine the final product is conjugated, so it also has significant stability. So that's why you can't conclude very fast that, sir, aliphatic amine will do reaction very efficiently, aromatic amine will not. In this case aromatic amine reactivity is less because the lone pair of this nitrogen is involved in resonance, but ultimately final product is conjugated. So that's the reason of stability. Now there are another kind of amine derivative, that is hydroxylamine or hydrazine, and by the way student, remember this hydroxylamine remains stable as means its salt form, and hydrazine also salt or water adduct. Now question is primary amine versus hydrazine, who is more reactive for Schiff base formation? The answer is hydrazine, because in hydrazine there are two nitrogen, adjacent nitrogen, and they have lone pair, and they lone pair repulsion, and this is called alpha effect. So that's why this is more nucleophilic, or you may consider better nucleophilic, okay, because of this lone pair repulsion. And what is the step? Actually nucleophilic addition, then water elimination, the Schiff base formation, two step. First step is nucleophilic addition, so in first step this performs very efficiently. So that's why in reality these hydrazine hydrate react far more efficiently compared to simple amine or even primary amine also. So now what about the secondary amine? We have discussed about primary, secondary or tertiary amine. Actually this secondary amine reacts, but it, for example, if you take this cyclohexanone, what it will produce? You can expect that just there is one hydrogen, so what you can expect? there will be a cationic species. Just sometime before I told 2 hydrogen from amine and 1 oxygen, but in this case only 1 hydrogen left, so there will be a positive charge and some X minus will be there, counter anion. So this is, and by the way, this is not actually Schiff Base, student. This is another type of compound that's called enamine. And you can see after protonation deprotonation of 1 hydrogen from here by base, it produces this, means this enamine. So this is a different chemistry. What about the secondary amine like pyrrolidine? And in case of tertiary amine, there is no NH bond, so reaction can't happen. So this is gone. Please remember this. Now, a simple question may come in your mind that why do we see so many negatively charged species in basic medium but positive charged species in acidic medium? A simple question. See, basic medium means there is excess amount of OH minus, means excessive, means, and in case of acidic medium there is significant amount of H plus. Although you can say that, sir, you can't take OH minus only, there is some M plus, it's true, or in case of acid there is X minus, it's true, but property is reflected by this H plus, means in acidic medium more H plus is there, means conjugate base, this is stable, so this X minus or M plus is stable. So the reactivity is reflected because of either this H plus or OH minus. So whatever medium we will take, that if you take basic medium, this anionic species will predominate, and if you take acidic medium, then this cationic species in this proton will predominate. So that's the thing you have observed sometime before in the reaction mechanism. Now, in conclusion, this Schiff base formation is a simple condensation reaction between carbonyl, mainly aldehyde I told, with amine or mainly primary amine. So in this case, they do this condensation and they will produce water, and for that purpose, please remember catalytic amount of H plus or OH minus needed, and you need to do workup to get the final product, that is the Schiff base or imine derivative. Now, an important question comes, can Lewis acid act as catalyst for Schiff base preparation? Actually, yes, because Lewis acid has vacant orbital which can accommodate lone pair of electrons. Now, if you look at these two, this is aldehyde and this is amine, both have lone pairs of electron. You can see lone pairs of electron here. So, question, if you take a Lewis acid, then which can coordinate to the Lewis acid efficiently? Obviously amine, because the electronegativity of nitrogen is lower, so the donor capability of nitrogen is higher, because this lone pair is donated to the Lewis acid. So after donation, the parent atom, means for example either nitrogen or oxygen, whatever you say, gets some formal positive charge. So ammonia Lewis acid binding is very efficient, but it will not result anything. But if these lone pair of electron from oxygen and Lewis acid make adapt, then what will happen? There will be electron deficiency on oxygen. Consequently, the electron deficiency of the carbon will increase. Now, if we present this thing in a relatively better way, what you can expect? This is O, this is Lewis acid, and after donation there will be a formal negative charge on Lewis acid and formal positive charge on oxygen, and through a canonical, means resonance, you can represent this thing that it can come here. So here oxygen, here Lewis acid having minus, and this carbonyl carbon having plus. Similar like acid catalyzed, this similar type. So Lewis acid can also do the same reaction, and following a similar type of reaction pathway, it will end up in imine formation. So Lewis acid can also act as an catalyst, because Lewis acid participates in the reaction, but ultimately it remains unchanged. Now let's come to the application of this Schiff base. First one is ligand preparation. See, just trick, remember what I told, oxygen to hydrogen. So one side is imine. Now why 2? Because there are 2 amines, so another same, so that's why 2 written. So similar reaction will happen, and ultimately it will produce this salen ligand. This ligand has a name, it is called salen, and this is ethylene diamine, that's why this is called salen. Now a question, what is the denticity of the salen ligand? I request you student, pause the video and write your answer in the comment box. Means how many centers are there in the salen ligand which can coordinate or bind to the metal? So this is the question. Now, so it's a ligand. Ligand means it will coordinate to the metal, and that metal centers can act as catalyst. So first learn about this. Now here you can see this part, I guess you are familiar, but why this is protonated or ammonium plus, and this is why this acid? Actually remember student, free amine free amine, I have a tendency to get oxidized. So in presence of atmospheric oxygen also, so they can oxidize, and we don't want that. For that purpose, if you want to keep the amine safe, you can make it as a salt. So this is nothing but a salt, and if you treat this salt with base like this K2CH3, it will regenerate the amine in the reaction medium. So overall this reaction is happening in the slightly basic medium. So K2CH3 is a weak base, sorry. So similar fashion, so this is one oxygen. In this case, there after this reproduction NH2, 2 hydrogen, and ultimately it will prepare this salen ligand just sometimes. So there is a difference, two bulky groups are there. So this gives the final material selectivity. So in this way you get this salen complex. And now please look at this center and these centers are asymmetric. So reaction of this with manganese acetate, better to say manganese 2 acetate here, produces this Jacobsen catalyst. Now I request you student pause the video and write what is the oxidation state of manganese in Jacobsen catalyst. Okay, so this Jacobsen catalyst actually used in Jacobsen epoxidation, and actually the oxidation state of manganese is +3. Why +3? So just look at this example. Here oxygen is used, so this is actually oxidizing in nature. So that's why manganese 2 center is oxidized here into manganese +3 center in the Jacobsen catalyst. Now what is the Jacobsen catalyst actually is? It is a coordination compound of manganese and salen type ligand. It's a coordination compound, tetradentate ligand, and it is used in asymmetric catalysis. I shall explain in the Jacobsen epoxidation. So epoxide which is produced, that is asymmetric, or you may consider this is a chiral epoxide. So this is also a chiral synthesis. I know you people are very much interested about this chiral synthesis, so this is one of the example. And for here what happens, the enantioselectively alkene is transformed into epoxide. And by the way, I have already discussed other methods like allylic alcohol oxidation, surplus asymmetric oxidation, even other also like urea hydrogen peroxide, MCPBA. You may visit for those epoxidation reactions also. Now here what happens, these manganese catalyst, see this alkene react with aqueous sodium oxychloride in Jacobsen catalyst in DCM as solvent. This is dichloromethane and produces this chiral epoxide. How this reaction happens? Remember student, this alkene is the reactant, and which one is the oxidant? Oxidant is sodium oxychloride, and it converted epoxide. Why sodium oxychloride is an oxidant here? Because the oxidation state of chlorine is +1 here. But remember, halogen prefers to go to -1 oxidation state. So 2 unit electron, 2 unit oxidation it do, 2 unit electron it take, and it form this -1. So that is the reason why this sodium oxychloride act as an oxidizing agent. And what it does, it oxidizes the catalyst from +3 to +5. And we know this is a oxo species, manganese oxo species is very reactive. That's why it selectively react with this alkene and ultimately transfer this oxygen to this alkene, and that's how the selective epoxidation happened. So this is the catalyst. Now why asymmetric material, means why this reaction result in chiral epoxide? That question is answered here. Now just look at student about the substitution. This is why? Because bulky. So epoxide alkene cannot approach from this side to the metal center. So not possible. This side chlorine is there, so it can't approach the metal center. That's block. Fine. There is only one option left from the above side where oxygen resides. Now I guess you understood. Now question is, this is manganese +5 species. Okay, and just look at this center. These are asymmetric center, these are asymmetric center. So that's why through particular way this epoxidation happens. Means the catalyst environment is chiral because of this salen ligand. So that's why we get enantioselective epoxidation. Okay, so I guess you have understood that why a particular epoxide got preferred or produced in excess, means enantiomeric excess. Now another example is related to Nobel Prize in 2021 by Professor Ryoji Nayori. Okay, so he developed a copper Schiff Base complex for the metal carbenoid complex cyclopropanation of styrene. but here you can see the asymmetric centers. Similar here, this catalyst is actually, you may consider this is a chiral catalyst. So since it's an chiral catalyst, so it results in enantiomeric excess C. Okay, so that's the interesting thing, and this work is related to 2001 Nobel Prize of Professor Naori. And remember, this Schiff Base also used in metal organic framework or MOFs, but I will not explain in this video, it will be too much long. But let's discuss another very important thing, that is covalent organic framework preparation using Schiff Base. These covalent organic frameworks are the class of material that can form two-dimensional or three-dimensional structure through the reaction between the organic precursor, resulting strong covalent bond to afford porous stable crystalline material. So you may consider in this case, this is actually a metal free polymer or covalent organic polymer or carbon based polymer. So this is actually a polymeric material from this monomer. This is, so what happens, just remember the concept, oxygen to nitrogen remove. So in this way imine bonds are formed. Since there are 3 aldehyde, so 3 oxygen, 3 amine, so in this way this reaction happened and it resulted in a hexagon type structure. So I am not going to details more, student, you may be confused, but and how the reaction is happening, 5% acetic acid, just I have explained the mechanism of acid catalyzed Schiff Base formation, similar pathway is followed here. And this material is very famous, it's a future, means in future it will be used extensively, which I shall discuss a dedicated video in future. It could be used as a catalyst, it could be used as a photovoltaic material, dye, drug delivery. In almost every field such kind of material are used, and such materials are important from green chemistry point of view because it is a metal free, so less toxic for the environment. So in conclusion, what we have learned, it's efficient reaction for imine preparation and the product is very stable compared to the carbonyl, means relatively more stable compared to the carbonyl derivative, and the reaction happen by nucleophilic addition and condensation, and ultimately water removal happen. Condensation means water production during the reaction. Now this is an efficient method for ligand preparation for metal complex. I have shown Jacobsen epoxidation, and finally it's a technique for cheap and green material preparation like covalent organic framework. Now let's come to our today's question, MCQ. What is the product? See student, this is carbonyl, this is amine. So what will happen? It will produce a imine. What is the structure of the imine? Just same strategy I have told you sometime before. What? Oxygen and these 2 nitrogen eliminate, it will result in imine. So this is the imine, and we know borohydride can reduce. Actually this is a decaborohydride, you may consider. So it can activate and subsequently this hydrogen could be transferred here, and in this way it will open up. So ultimately what it will result? So first of all, here these will attach to hydrogen, this is the nitrogen attached to boron having negative charge. So this is the aryl group, means paramethyl. Now this after workup means in methanol. So what it can do, this nitrogen can abstract proton from methanol and ultimately it can produce this, means after workup it will prepare this. So, and by the way, if this methanol is a subsequent, generally what happens after reaction, people do workup, means basic water workup. As this amine, we need to get the free amine, so under basic condition you will get this product. So this is the answer. Now question is, why not this? This is the simple reduction of ketone. Remember student, this Schiff Base formation is a very fast reaction, and this boron can act as a Lewis acid. See, this boron can act as a Lewis acid and it can form coordination with ketone. So that is the method I have just sometime before explained, Lewis acid mediated reaction. So in this case it will produce this alcohol and ultimately this will result in the final product. So this is the end of the discussion. Thanks for watching. So if you really enjoy my teaching, please help this channel to grow, and if possible you may visit my another channel, that is Climate and Chemistry, where I upload global warming and climate change related videos.